All right. Good morning, everyone. So for those here in Athens, as we're finally able to use our computer lab again. This was flooded in the week prior to class started, and it was only finished, I guess, this week. So I'm glad that we're able to get in here now. And just so you all know, just for those in Athens, all of our class peers are going to be here, regardless if it's lecture or lab. They're all going to be here. That was the plan originally, and we had to adapt. So no more classes in the conference room, no more classes on the 3203, I think. It's all going to be here. Okay, so let's talk a little bit about the assignment, right? That was due last night. So all of you turned in on time, so thanks for that. I appreciate that. As we discussed, we're going to be using the files that you produced in the next steps, and this is how it's going to be for a lot of the upcoming assignments. Is we're going to do something in class. I'm going to share with you another data set. You're going to have to repeat what we did in class with the new data set. This is going to happen a lot. So really, I want to make some comments here just to clarify, because I noticed that perhaps I wasn't super clear in some parts. So really, what I needed. Let me just do something here on the video. That's this. So what I really needed from you to submit me was, let me just come here and open one of the submissions just to show you. Okay, let's try this one here. So this is one of the submissions by one of the students. Really, the only thing I needed, and most of you did this, was just to send me the summary, right? This is all I really needed from you. Of course, on your side, you were expected to do everything, all the coding, generate the wrangling, the cleaning, the editor, and create those outputs on your side, because you're going to need that. And I wasn't going to share that with you because you were producing them. But this is basically what I was asking, right? I know that some of you went ahead and used the same answers that I sent you and did all the coding in there. That was fine. It was probably not the most or the easiest way to do it. What I suggested, at least, was that you would basically have 4 new scripts, right? So 2 for each one of the sites, where you would copy and paste what we did in class for the wrangling and the editor for each one of the years. And you would basically just change the code to adapt to the new data sets. And in the end, it would have 4 new scripts that would generate the outputs we needed. And then I really only needed from you the answers like this. And again, most of you did that. And I really, on my side, I really don't care how we got to these answers. The main point is that you were able to produce the outputs and send me the summaries. That's all I needed. If you did do all of your coding in one script, that worked, that's great. If you did do what I suggested as far as having 4 new scripts and you added them, that was probably the most straightforward way. But anyways, I guess at that point is I just wanted to say what I was suggesting for you to do, and probably a way that would make things a little bit simpler on your side. Okay, and then I want to show you here. So this is basically the key of the answers. I will send you personalized feedback later. I know that, again, the majority of you were able to get to these summaries, to these exact numbers. Maybe 4 or 5 of you did not. In those cases, what I observed is that sometimes the minimum and maximum were the same, but the mean and CV were different. Maybe you did something a little bit different on your side from what we did in class. Maybe use a different quantile or something like that generated the results to be a little bit different. I noticed in one case, the answers were flipped. So the 2019 stats were actually reflecting the 2020 data, and the opposite as well. In that case, I just wanted to say that if that happened to you, just so you watch out to make sure that you do have, even maybe you flip the answers, but you do want to make sure that your files are actually matching what they should be, right? So if your 2020 is actually showing the stats for 2019, maybe just call that 2019 from now on. And it's probably just a flipped thing that happened there. But anyways, overall, this is what I was expecting. I noticed only later that I asked you to send me a Markdown file, a .md file as your answers. And that was actually something that I asked last year, and I forgot to just change that when I was asking for you to submit. I really did wanted the HTML. I know that I asked for some of you to send me the HTML render version of the QMD, but regardless of if you send me the HTML or QMD, that's, you know, that there's no issues there. I just wanted to say that I actually thought I had asked you to render and send me the HTML. Then I went back and checked, and I didn't ask. So that was actually my bad, that I confused myself, I guess, in that aspect. Okay, so I guess those were some of the points I wanted to share about the assignment. Does anyone have any questions or comments or maybe issues you ran into that you would like some clarification?
Yes.
Well, so, go ahead, Dennis. Yeah.
Go ahead. Yeah, so on my side, I think when I ran those mini Y minutes, I found like I had one of the negative, like the box was outside. That is why I thought like we are getting the minimum value from the minimum raw data of the minimum. I mean, from the raw data of the minimum. Like that is at 1.658 is the minimum value of the raw data. But I'm confusing myself, but I thought like after filtering, maybe I could not get that minimum.
Right.
I could get another one. But I thought like when I got like the quantize, the box was going out of the data, giving me a bit of negative values. Then when you go like putting the minimum, to get that one. So I don't know, maybe I did a mistake somewhere, but maybe you can take that later. Yeah, so
I don't know if people online were able to hear, but Dennis was just asking that for one of the data sets, the min Y was actually a negative value. So it was like lower than the minimum data point in the data, especially because it's EO data. So we wouldn't expect to have a negative EO data, right? So I didn't redo this whole thing myself this year, but when I did last year, I think that was the case. I think for one of the data sets, we do get a min Y that is negative, right? So I mean, you know, of course, we wouldn't expect to have negative values anyways, but if you still follow the script and you apply that filter, what's going to happen is basically going to filter all the data on the lower side, on the lower end of the data, right? It's not going to filter minimum values anyways, because the minimum that you're given it is already below the minimum in the data. Does that make sense?
Okay, my question was then on the filter. Like if the filter can give you the negative value, it means the filter somewhere is wrong. So then I started thinking like maybe the way they applied the 50%, like you take 25% of the 50% of the 50 quantiles, you see. I think maybe we would be dealing with the negative, I mean the lower side, like the 0.25 of the lower side and the 0.25 of the upper side instead of the middle one, middle data, which is 50%.
Yeah.
Maybe that could not give us the value anyway, because I think sometimes when you take 0.25 of the 50%, you get a big value more than the lower side of the side.
Yes, that's exactly right. And that's so, yeah. So then Dennis was just clarifying the question as far as if you're using the formulas that we applied from the paper of using 25% of the difference between the upper and lower, that number, so the min Y in that case or max Y could be below the range of the data, right? So that could happen. And let me tell you why it happened specifically with the data sets that you were working with. If you were plotting the data as you were applying the filters, you may have noticed that some of these data had already been filtered before getting to us. Right. And so in that case, if you think of it, if you take a data set that's already been filtered and then you try to filter again, that is expected to happen because now your data already is shrunk to some extent, right? So you already cut off the tails and then you're trying to cut off the tails again. So that's what kind of pushes your limits to be beyond the data. And this is also brings up a really interesting conversation about like keeping track of data and what has been done to data before it gets to you. I'm sure that if you're going to be working on your research, if you're going to be working with producers, data is going to come to you. And sometimes you don't know if that is the completely raw version of the data or if something has been done to it already. In some of these cases here, I think it was, I don't remember which year it was, maybe 2019, but was already filtered before. I mean, when I gave it to you, it had already been filtered. So you would have already seen some gaps in the field. And the point is, I don't know what was done to the data before it got to us. I don't know what type of filters they used, what type of values they used. So it's just coming back to the point of reproducibility, right? Of like, if we're doing things in programming, using programming languages, and I ask, hey, Dennis, the data you share with me, what was done with it already? You can just send me the script and that's documentation of what you did already, right? So just doing as we're doing in class and learning how to program things and using the program as documentation itself for what's been happening with the data, it's a big point that I want to make with this class. But yes, that's a great point. You know, I guess just going back to your question then is that, yes, in the min y and perhaps even max y could be above or beyond the data if the data had already been filtered. Now we're just trying to, again, cut the corners where maybe the corners are not there anymore. Not the corners, but the tails, I guess. Yeah, that's a good point. Yeah, did you have a question?
Yeah, I was gonna ask, is it okay if we just typed those numbers out in a chunk and submitted that in the HTML rather than like just pasting that table into HTML, you know what I mean?
Yeah, I mean, different people submit it differently.
Okay.
So what you could have done is, you know, you could have, I mean, I didn't try to do this myself, but let's see if I just like copy this, because this is a chunk output, right?
Right.
But like if I just, yeah, if I paste here, it doesn't look good.
Okay.
So what some people did is they created, so on the clean versions that you all created, right? What I saw maybe a couple of people doing is on the answers, they basically just read SF on those data. And then they produce just a very simple small piece of code to give the summaries on the answers. So it was already showing as a chunk output.
Okay.
I mean, I think the one that I showed you was actually that.
Right.
But you could have just like copied and pasted. I mean, as long as you format it properly, so it's understandable, right? I guess that could have been, so it could have been as part of a chunk output, or it could have been just outside of the chunk as like just regular text.
Okay, great, thank you.
Yeah.
So in order to get like it to look like that on the assignment, did you have to save it as like some sort of data file and then just input it into the assignment?
So what the student did on the one that I showed, so he basically just read in the clean versions of the GeoJSONs that you all exported in the end. So they just brought that back into the script with the answers, and just did like a summarize function, just like we did in class on those. Yeah, so it wasn't an extra file, it's just the same file that you all created. Yeah.
I tried to play around with it. I think I was trying to do extra steps that didn't get done.
Yeah, and I mean, and really, again, like if anyone did extra steps, as long as you got me the answers just, you know, in some format, either as a chunk or maybe as just text, that's what I needed. So extra steps, you know, if that helped you on your side, then great. But yeah, nobody is like gaining points or losing points by doing one way or the other.
That was my question. I was gonna say I typed that. I need to read.
No, that's perfect. Yep, that's perfect. Okay, so online, does anyone have any questions about the assignment, the answers, the process?
Yeah, I have a question. Can you hear me? Did you hear it? Yeah, I did.
All right, I don't hear anything, so I guess we'll keep going. So this immediate next exercise is not gonna yet require the file that you created, but we will probably either sometime today or Friday. And in that case, I will provide you, send you the feedback. I mean, you probably are, at this point, you already know if you got this right or not. If you did not get it right, I will be reaching out. And then, just so we can try to see what happened and maybe get to those same numbers. Because again, we're all using the same data. We should all be using the same code. So we should all be getting the same output, right? Reproducibility. So if you didn't get the same output here, I'll be reaching out to you for us to chat. Okay, so let's get started with today's exercise.
Sorry, Professor.
So I already went ahead and launched my project. If you have not done that, please do so. And just there's some scripts. Oh, I actually have the wrong project.
It's the same project that we're working on, that little project.
Yes, it's the same project. So that's going to be the 04 yield monitor. Yep. Yes.
Hey, somebody texted me and they said that, Griffin is trying to talk to us and ask us questions.
Oh,
I don't know if they remember this.
thanks, Tanner. So is Griffin, sorry, I just, Tanner just brought to my attention that Griffin is trying to communicate, but I guess we're not, at least I didn't hear anything on my side. Can you?
Can you hear me, Professor?
Yes, I can hear now.
Yeah, I had a question about the buffer boundary.
Mhm.
So while I was doing the assignment, especially in 2020, so I noticed that on western side of the field, some really good yield points data were being filtered out. But what I tried to reduce the boundary size from -20 to -10, -15. So what happened, like on the other part of the boundary, let's say eastern part, so
Mhm.
the borderline effect, they were being included in the data. So is there a way to like modify that buffer, like we do in QGIS, we really draw the buffer along the boundaries. Can we do something like that in R?
So you mean like to have different widths of the buffer depending where you are in the field? That's your question?
Yeah, you could say that. We can modify the buffer according to the field. So we really only eliminate the points that we know like are erroneous.
Yeah, so for our exercise here in class, I guess, so I think it's really awesome that you are like looking that and checking that, because that's really what we should all be doing when it comes to any data that we do in real life. In class, I wasn't expecting you to do that just because that would create differences in the final data set that you all produce. And I don't want that to happen, right? I want you all to have the same data in the end, so we all get same results moving forward. But Umar, what you did, that's perfect. Well, sorry, is that Umar? Yes. Umar, what you did is really what I guess any of us should be trying to do when we're doing with data that, you're working with for your projects or whatever it is. I guess to answer your question, the best way, at least that I know of, to address what you're saying is to go back and redraw the original boundary. So it is closer to the points to begin with, right? So you don't have one side that is the boundary is closer, and on the other side, the boundary is farther away from the points. So the solution would basically be to go back and redraw the boundary and then do the filter based on the boundary that is more constant, I guess, as far as how far it is from the points. Does that make sense? Awesome. Yeah, thanks for the question. All right, anyone else had any question about the assignment? Okay, I don't hear anything, so let me let me go and launch our project so we can start today's exercise. Okay, so again, I'm launching the yield monitor project. And what I'm gonna do is again, come on the Files tab, go on my code folder and then launch the interpolation partial script. So this is what we're gonna be doing today is the interpolation. Let me increase my font size here. All right. So again, this is something that I think I asked you to do on Sunday to move the interpolation partial script into the project. So I am assuming that you already have that. If you don't have, you can take a moment to catch up. This is on GitHub. It's been there since Sunday. It's just on the class code folder, and it's the interpolation exercise. All right, so let's get started here. So for today, what I expect for us to get out of this is first to talk a little bit and learn why interpolation is needed and useful. We're going to explore one type of interpolation analysis that's going to be the inverse distance weighted analysis, IDW. It's probably one of the simplest, most common interpolation techniques that is used in precision ag. We're going to perform IDW on the yield data set, and then we're going to extract interpolated yield data based on a grid and then save that to file. Okay, so if you go to the first chunk here, the setup chunk, I left you 3 packages that I believe, maybe you already have them, but maybe already have stars, but just to make sure, if you can just uncomment the first one, run it and install it. And then once that's done, you add a hashtag again and do the same for all 3. And also just to remind everyone, playing the all chunk, it can be very useful. However, when you are installing packages like this, I do not recommend that you do the play all, because that can get things cluttered. And if some error happens, you're not going to know where that's coming from. So my recommendation is to uncomment or remove the hashtag. And if you have your cursor anywhere in that line, you just, on a Mac is Command Return, on a PC, I believe is Control Enter, just to run that line of code itself. So that's a shortcut that I use all the time. So please go ahead and install those 3 packages. I do not anticipate you having issues installing them. It should be pretty fast and no errors. If you do have issues, let me know. So once you install all 3, then you can, make sure again, always.
Hey, Dr.
Yeah. Yes.
Dr. Yeah, really quick. So under like the library stars, I'm getting a load required package A-bind. Like, do I need to install that package?
I think it's just telling you that is also loading that. So I don't think it's an error. It's just probably a warning. Let me see on my side. Yeah, I get this thing. So yeah, that is just a warning. It's just telling you that is also loading other required packages.
Okay, awesome. Thank you.
Yeah. Oh, and also something else I wanted to mention to you. So this, I guess this piece of the code here on the top, if you want just to delete that, go ahead, because that was something that I forgot to delete before sharing with you. That is just to set up some chunk options, but that was before when I was using RMD files, so R Markdown files, which we're not using anymore. We're using Quarto files, QMD. And just a quick tip here, really for all of your scripts. Sometimes I may forget to give this to you already, but just for you to keep in the back of your heads, especially for the mini project, this can be useful. So we know that some chunks produce messages and warnings that we don't really care about. We care if it is an error, right? We want to know if there's an error because then we have to fix it. But if it's just a warning like the one that stars was given here, now it's not given anymore, but it was before. I know tidyverse also gives a whole bunch of warnings, and when you render that, those warnings come on the render file. If you want to suppress that, an easy way to do is if you come in the beginning of the chunk and you type hashtag and vertical pipe, and you hit tab, there's gonna be a whole bunch of options that you can change for that chunk only. The one that we can change to suppress those messages is message. So there's one chunk argument called message that we can just set to false. And sometimes you also need to set warning to false. So this is just, especially when you're rendering things, you want to make things look more professional and not have a whole bunch of warnings that don't make sense to someone that may not be familiar with R. You can just change those two options on the top of the chunk. And these will only apply to that chunk. So it's not a global option that you're setting for everything. All right. Yeah, so if you wanted to set it up for the whole file, we would have to be on the YAML part of the script, which is this top part here, which right now we're really not changing anything. And maybe we should, but for now, let's just leave it at that.
I was just saying, for instance, if you just wanted it to not show a warning.
Yeah, no, absolutely. It will have to be up here. And I think we've done that in a previous script as an example, but yeah, so let's say another case that you may want to suppress something for the entire script is, let's say you're sharing this with someone that doesn't know R, doesn't care about R. They don't want to see code. You just want to share with them plots and tables, right? From the script. There's an option that you would set at the YAML level that you can suppress code altogether. So no code will be shown, just output, right? And really some people write like publication papers in QMD as far as like everything there, all the narrative, all the tables, citations, everything in here, and just suppressing the code from appearing on the final paper. Yeah. All right, so if you have already installed the 3 packages, you can go ahead and run again this chunk. And now the first thing that I want to do here is to bring in one of the yield data sets, right? So the clean yield 17 data set is one I want to bring in here. If you recall, you exported that as a GeoJSON, so it is a geospatial file. So you probably know that to bring that in, we need to do a read_sf. So on my computer, at least, the way I save this, and I think was what I proposed you saved as well. I have that in the data. So again, we're on the 04 NAS monitor project, right? And the goal was that on the assignment, you exported those data layers to your data folder of this project. Assuming that's the case, I would first say .. to get outside of the code folder, hit tab, get into the data folder, hit tab again, and here I would have the EO17 clean.geojson, right? So this is what we created in class. So you should have this one in this folder. For the next ones that you created, so the 19 and 20 that you created through the assignments, if you did export that to a different folder, please make sure you move them into this data folder of the 04 EO monitor project so you can have this easy access to it. Okay, so just reading in that file and just printing here to see the initial rows. So it is, as we already know, it is that one that has 27,000 rows. It's already been cleaned. So this, if just to refresh your heads, the EO17_clean is the one that's being wrangled and cleaned already, right? So it's been through a couple steps of processing. And now the next step of processing is going to be to interpolate it. Okay, so just as always, just doing a quick summary here, just so we confirm that our yield especially doesn't have any NAs, that the minimum and maximum makes sense. Just some quick exploratory data analysis. I always recommend to check your data when you bring it in, even if you know it has already been taken care of. Now, the next thing, let's just go ahead and bring in the boundary. I want to call that boundary W already. I left you the object there. So we use the assignment symbol. As you know, it is a boundary, so it is a vector file. We use the read_sf for that. Open and close quotation marks. You want to get outside of the code folder, get inside the data folder, and bring in the boundary.geojson. In the past, well, we can just bring this and print it. You're going to notice again that when we bring it in, it is in WGS 84. because we're going to be doing, so every time you do something related with distances, right? So if you do a buffer, that is based on distance. If you do interpolation, which is what we're going to be doing, which is based on distances as well, we do want to have everything in a projected CRS, which WGS is not projected, it's geographic. So let's just change that on the fly here, adding a pipe right after the read SF. And let's just say, as we've done in the past, use the function st transform. And then it has an argument called CRS, and the value that we want to give it to be UTM NAD83 zone 16 north is EPSG code 6345. So now if you rerun this entire chunk and you print it again, and you go to the first panel of the print output, you should see now projected CRS in the CRS that we specified, right? So now it's in a projected CRS that the units are meters instead of degrees as it was before when it was WGS 84. Okay, so let's, I think I left you all the code in there already for this next chunk. I just want for you to run it, and then, so we're basically creating a map using ggplot of the, again, of this layer, right? So it's the one that's been wrangled and cleaned. And I just want to have this up so we can see it and we can talk a little bit about interpolation. So why do we need to interpolate? I guess, let me put that question up there and see if anyone has any thoughts. Why would you need to interpolate this map that we're looking at right now? Any thoughts?
Because we have empty space.
Okay, so Shekar mentioned because we have empty spaces. Yes, Amrinder, you're gonna say something?
Like to make it like more like raster file because it's point it out.
Right, so it is point, yeah, so Amrinder brought up an important point about it, that it is a point, even though from this distance, it looks like it's pretty continuous, but we know from zooming in and from previous classes that this is a point shape file. So what happens is, let's say, if you're gonna make some precision ag decision with this map, and you happen to be in a place where there is no data, then you have no prescription, right? We need a continuous layer of data. So we need to fill in the gaps of this data set using the data around them. So we have a continuous layer that can be used for precision ag or any other purpose that is geospatial. Perfect. Thanks for helping out. Okay, so again, there are a couple, or maybe more than a couple. There's a handful of different interpolation methods. Again, the one that we're going to be using is called inverse distance weighted. IDW is the acronym for that. Is it deterministic? And basically what it does is it goes into a point of the field and it uses a given distance of points around it to decide what the point that we don't know the value of should be, right? So it's taking into account distance to decide how much weight different points on the field are going to have on deciding what is the point that we're trying to estimate in a given part of the field. That's kind of what inverse distance weight is using. You probably also heard of kriging. So kriging is a statistical method for interpolation. It takes into account the semi-variance of the data points. We're not going to be talking too much about that. And we're not going to be using, at least not for this exercise, but I just wanted to bring this to your attention as well, because kriging and IDW are two of the most common interpolation methods. And again, we're going to be using IDW. So I want to launch here on my side, and you have the link on your side in case you also need to do this at a different time. But I want to show you this website here, which has a it's basically an online book that was produced based on, it was produced for geospatial analysis in R. So it has a lot of the theory, but also the code to apply what they're saying. And what I really want to show you here is just what this book shows very nicely. So, in this case here, let's say that this could have been like a field where you went and soil sampled. right? And then, so you do soil samples in specific places of the field, but then you have gaps in between the points that you didn't sample, right? So interpolation helps us to use the points that you did collect and fill in those gaps with using a statistical algorithm. And again, in our case, that is IDW. Let me see here. Yeah, so this is another example where we have points and interpolate them, and then you have a map. And also with IDW, it's very common to see this pattern here that is called like the bull eye, where you see even on the interpolated map, you see these like hot spots, and that's basically because you have one data point that's probably controlling most of the interpolated points on the interpolated layer. And then you really see that stand out. So that's a feature that we see a lot here. Let me just take a look at my script and see. Okay, I think this is a good point to make this discussion here. So a really key point I really want you to take away from this class, which we're not going to be doing ourselves, but I do want you to keep in the back of your heads, is, you know, interpolated maps, pretty maps, easy to do, very easy to do. The problem is how those maps are being produced and if they have some way of you knowing how reliable they are, right? So I just wanted to give you an example here of, so this is using IDW and just changing the power of IDW. So this basically controls how many points and what's the radius that you will accept points to contribute to a point that you're interpolating. This is one of the arguments that it has on the function. And I just want to show you here that with the same data and again, IDW, just using comparing one algorithm, we're just changing one of the arguments, that's the power argument, and look at how the maps change, right? So your output is changing, the interpolated map is changing depending on, first, in this case, would be an argument of the IDW itself, but also if you're comparing different types of interpolation methods. So if you do IDW and Kriging, you're going to have two different maps, even though the original data is the same, right? So just keep that in the back of your head, and you know, because this is important. Just because you see an interpolated map, ask questions, ask how was it done, how many points were in that original map to begin with, so we understand a little bit better the quality of that map, and not just because it's a pretty map with colors doesn't mean it's a good map. Yes, both.
So in those maps that we're looking at right now, the little plus signs, those are the actual data points.
That's right.
So there's actually quite a bit of space right there in the middle that's actually not.
Yep, that's a great point. Yeah, so Bo was asking, like, so the crosses that we see here are the actual data points, and there are places on this I don't know, field or whatever it is that there are no points, right? So that's a really great point, because interpolation is going to interpolate regardless if you have 100 points near or 0 points near, right? So it's really a key point. And again, what I'm trying to drive home here, the message is, with the same data, you may get very different maps depending on how you interpolate, right? So always keep that in mind and be suspicious of an interpolated map that you don't know anything else about it, because it could be, you know, it's easy to create a map. It's not easy to create a good map or a good interpolation map.
But I see like also the regions values are changing based on those weights. So
Yeah, so the P here stands for power, right? So it's basically it's the power of how many points is taken into account to come up with an interpolated value. So that's what's contributing to the differences that we're seeing as well. And also here, just coming lower, so this is actually comparing it. So above we were comparing one algorithm, just changing the argument of that algorithm. Now they have here showing 3 different algorithms. So inverse distance weighted, which is what we're using, versus ordinary Kriging versus universal Kriging. We're not going to get into details of Kriging itself, but again, the point I'm trying to make is, if you change your algorithm, you're changing the way the map looks, and not just related to how it looks, but you know, what decisions you're going to be making based on this map. So that's also something to keep in the back of your heads.
so it means I may get like different values of views in a map because of changing the power.
Yes. Yes. So there are ways, I'll be right with you. Well, there are ways that we can do to check the quality of a map. We may see some of this towards the end of the class if we have time. It's basically going to be using some machine learning concepts to do cross-validation. That's one way that we can do with IDW and know better what is the best option for you to use for that specific data set. But today we're not going to be checking that. We're just going to be using IDW normally without really playing with its arguments too much. Yes, Emma.
That's kind of what I was gonna ask, is like, how do you pick which one to like start using?
Yeah, so so the reason why we're using IDW is because it's the simplest one. And it's probably what you're going to come across the most in your careers. Kriging would be the next step, would be like a little bit more complicated, but probably a better option because it takes more into account the spatial relationship that the data has instead of just taking distance into account. If we were to do Kriging, we would have been able to actually, so Kriging produces you an error map as well. So it produces the interpolated map, but also an error map that gives you an idea of what is the error in certain parts of the field, which can be used, to some extent to understand what parts of the field maybe you could go back and resample again. So let's say if it is a soil sample that you're doing, Kriging is going to tell you, hey, this part of the field here, we have high uncertainty. Maybe go back and take some more samples and reincorporate into the data and rerun it so we can lower the error in those areas. But as far as comparing across different types of algorithms, it has to be with some type of cross-validation technique that, again, we may see towards the end of the course if we have time, but we're not going to see that today. Yeah, thanks. Anyone has any more questions? Yeah.
So like the value of P ranges from.
So P, I believe, is the power of, if you think of like a quadratic function or maybe a cubic function, P is that power, is the 2 or 3 in that. So really can go, I mean, I don't think it has, the lower limit is probably 1 or 0, but the upper limit, I don't know if it has an upper limit. Yeah.
Is there any maybe recommended P to use in case you don't know anything about those P's because they are producing different values?
Right. So so Dennis is asking if there is a recommended value of P. So we can look into the documentation of IDW function because they do explain there. So when we use it, we're not going to be changing P, at least not this exercise. We're going to use the default value, and I believe the default value, it's either 1 or it's calculated. No, I think it's 1. I think it's 1, but we can look into the help of the IDW function and see what it is. Yeah, I guess it's one of the things that you have to play around with cross-validation. And again, cross-validation is really the key here to understand what's the best way to do this properly. But if you're doing this as a quick step and you don't want to be playing too much around with it, just using the default options are normally okay, as long as you know what they are and you can report on them. Yeah, normally I don't, unless it is an actual machine learning paper, normally people don't play too much around with the B if they're not trying to create a predictive model to interpolate something. It's just like I use IDW and power was X. It's normally like that.
Better power is always not good because it's taking more points, so it could be more like accurate.
I mean, I guess it kind of depends, right? It will depend on the data itself. I mean, sometimes if you're just adding, you can think of it as a quadratic function, like just a plot of a quadratic function, right? If the shape of the data is quadratic and you fit a power of 10, that is just doing noise, right? It's not really fitting anymore the shape of the curve. So it's just that trade-off between model complexity and fitting the data properly, right? So it's a trade-off. All right, great questions, and yeah, I guess. Yeah, it was really great discussion. Anyone online has any thoughts or any questions about that? All right, I don't see anything. And also, so there's the link here, if you're really interested in this and especially exploring different interpolation techniques in R especially, I left the link here of this ebook on the script, but it's also listed as a resource on the class page on my personal website. So we have this resource out there if you're interested in reading more about it. Okay, so here's one thing that perhaps, especially if you're using point and click software, this may not be very clear, I guess. What is happening behind the scenes is that every time we do interpolation, regardless of the algorithm that we're using, we have to have a grid behind the scenes that we're using to interpolate over. So we have to create a grid, an empty grid that has no values yet, that is going to determine where a given point is going to be interpolated. And then it uses the actual points around it to determine what that value is. So the first thing here then is for us to go ahead and create this grid. We're going to create a grid in vector format to begin with. So if you come to the next chunk and use the assignment symbol, there's this very nice function from the SF package called ST. So every time it starts with ST, it's probably coming from either SF or stars packages. So ST underscore make underscore grid. That's the function name. What we give it is the area that we want to create a grid over. So in our case, this is boundary W. So you can go ahead and type boundary W. And then it has an argument, if you just add a comma, it has an argument called cell size that I want to say equals 10. And again, what unit is this number here? It is in meters, right? Because we transformed from WGS to NAD 83 UTM. If we had not transformed and boundary W was WGS 84, 10 would have been 10 degrees, which is not what we want, right? So that's the importance again of transforming, especially when we're doing things based on distance, is transforming your spatial objects to a projected CRS. So if you just run that and you just print it, which is below, we see here that we have over 6,000 features, meaning 6,000 cells of this grid. And they are of type polygon, right? So it is what we would expect, because you can think of it as just a grid, right? With a whole bunch of cells in it. And that's basically what it's telling us. If we just check the class of it, just so you can see, it is an SF object. So it is a vector. It is not a raster yet. It is vector. That's why we're calling grid underscore V. And I just wanted to make sure that we got that point. Okay, so the next thing I want to do here is just plot it, right? So right now we produced this object, but we haven't seen it yet. So let's just use, so if you just run this, this is the map that we created above, that we created a map and saved to an object called Euclid map. Because this is a ggplot, we can just go ahead and add a plus. So add a plus, hit return, and let's just add a geom here, geom SF. The data that we're bringing in is basically just the object that we created above. So that's grid underscore V. We can just go ahead and run this so you can see what it does. So this is our grid. This is how it looks like right now. I want to change a few things about it just so we can actually see the data that's coming behind it, which is the yield data. So if you come back to the code, add a comma, let's change the transparency. So that is done using alpha. So alpha equals 0.5 for 50% transparency. I want to also add a comma and ask for it to have no NA, to have no fill. So to do that, we do fill equals NA. And also I just want to decrease the width of the cell lines so we can see better. To do that, we say size equals 0.1. Now, if you run this, let me show you the code again. This is what we get. So one thing that I want you to notice here is, so we do have a grid, right? And the cells that we're seeing here have the size that we specified. So they have a size of 10. If you don't have to do what I'm going to do next. I just want to show you. So if I wanted to have a bigger cell, so a coarser grid, I could just change here. So if I have a coarser cell size, it means I'm going to have less cells for the same field or the same shape. So this is what we see now. We see bigger cells, right? And fewer of them for this area. I do want to go back and use 10 though. And, maybe one thing that you could ask me is, why are we using 10? I really don't have this is not set in stone as far as why 10 meters by 10 meters. this is a decision that whenever you're doing on your own projects, you can think about it like, what is the cell size that makes sense for me to manage, right? Imagine that perhaps you would be managing each 10 by 10 meters, so 3 by 3 feet as its own fertilizer rate or pesticide rate or whatever it is that you're recommending using this precision ag for. You can think about that. You can think perhaps of, what is the swath of the equipment that the producer has to implement this. Is 3 by 3 feet something that they can manage? Maybe not, maybe yes, I don't know. It's something that's going to be, related to their equipment as well. The reason why I originally chose 10 here, I just want to tell you, is I think it's a good enough size that we can see variability in the field. I think we have a lot of data points on the EO data to really have such a fine grid. So let's say if this was soil samples, and instead of having 27,000 data points as we do with EO, let's say we had 60 data points in this field, in this entire field, right? It would be a lot more sparse. Perhaps it doesn't make a lot of sense to make a 10 by 10 meter grid, because then there's a whole bunch of cells that are going to have 0 data points in or near them when we do the interpolation, right? So maybe that's also something to keep in mind. Here I chose 10 because, again, we have a lot of data points. Also because at some point we maybe bring in satellite imagery of this field to complement the yield data points that we have. And satellite imagery that we'll be using has the resolution of 10 by 10 meters. So it's going to be more closely match the resolution of other layers that we'll be using. But again, the number 10 here is somewhat arbitrary and depends on the things that we just talked about.
If you want to zoom out, you can zoom.
If I want to zoom out.
Yeah.
So this is not an interactive map as of yet, right? So I cannot really zoom out, but we could do this, on a map view. If we wanted to have an interactive map, we could use map view here. I'm not going to do that just because it's not in the script, but. Oh, you mean, okay, yeah.
Oh, you changed the size?
Yeah, I changed the size from 10 to 100. Yeah.
But what is the use of this size 0.1 that you mentioned? Why we use this one?
You mean here?
Yes.
So this is just for visualization purposes, right? It's just, so this, I mean, I can just show you what happens if we don't change that. This controls the size of the outline of the grid. So if we have it with the default value, it's just a little bit harder to see. So I just decreased to 0.1. So I think the default is 1. I just decreased to 0.1 just so it's easier to see what's behind it. But this doesn't affect any analysis, right? It's just visualization. This 0.1 here. The size that matters here is the cell size when we do the interpolation, when we create the grid, sorry. All right. Good questions, good discussion. Okay, so just to make this point again, is this grid right now is a vector file, is an SF object, and in R and perhaps in other software as well, we can only, for us to use a grid to make interpolations, that grid has to be in a raster format, which right now it's not. Remember, we talked about raster and vector before. This is in a vector format. So for us to be able to interpolate using this grid, we have to transform it to raster first. So if you go to the next chunk, that's what we're going to do next. We're going to save the result of this object called grid_R, meaning that it's now a raster object. We're going to use, so the first thing that we're going to give it is the data set coming in, which is the grid as a vector. We're going to add a pipe. So we're first going to use the function st_s_sf, just to make sure that now this grid is actually seen as a complete SF object. So this is what it would look like if we just print at that point. Now we add another pipe. We're gonna use a function called st_rasterize. So this basically takes a vector file and transforms that into raster. It has a couple of arguments here, that is dx and dy. So that is basically the distance that you want to have your cells in the raster. we're just gonna use the same distance as we used when we created the grid. So dx is gonna be equals 10, dy is gonna be equals 10 as well. So if we do this, it would basically be the same as the above, but in a raster format. What I want to do in the next step in the same code here is something that perhaps I forgot to mention up here. So every time, I'm just going to come back to this map and make a point that every time that we make a grid, yeah, as you can notice, the grid is not only covering our boundary, right? So we use the boundary to create the grid, but the grid is actually extending outwards of the boundary as well. And the reason for that is the grid basically takes the bounding box of this shape. What is a bounding box? It's basically, if you imagine, is a box that it goes to the maximum value on each one of the sides of this map and encompasses all the field, right? So this bounding box here is coming all the way to the left because that's the leftmost point, is going all the way to the top because of that point, is coming all the way to the right because of this point, is coming all the way to the bottom because of this point. So it's just a box that's comprising the entire field and is rectangular, right? So it's not going to be the shape of the field unless the field is also rectangular. So but that is also not what we want, right? Because I don't care for interpolating points that are outside of the field. That makes no sense for me. I have no interest in that. So let's clip or maybe crop this raster here to be only within the field for us to do the interpolation. So you come back to the code here, you add a pipe, and then there's a function called stCrop. And we're gonna crop. So this is basically gonna crop the raster to something, and that something again is our boundary underscore W. So if you do this and you print it, now one thing that you're gonna notice is that this is not an SF object anymore. It is a stars object. So we changed that. If we print the class here, maybe that's more clear. So it is a stars object, and stars objects are printed a little bit differently than raster objects. So we don't see the data frame as before. And one reason is that now we have cells that have different values within them. So we do get a summary of what those cells are, which right now, those cells are just the ID of the cells. So it goes from 1 to 6,000 something. And I mean, it's really not useful for us to look at the summary anyways because of that. But just, I guess the point is that raster objects or stars objects that are rasters print a little bit differently than vector files that are SF. Okay, so again, we transformed that grid from vector to raster, and then we crop that to be only within the field. Let's go ahead and plot this. So if you come to the next chunk, again, we're starting off with the yield map that we created already above. You can go ahead and add a plus there. Now, so up until this point, we've used geom underscore SF to plot vector files, right? To plot SF objects. Now it is a star object. It has its own geom. So it's called geom underscore stars. And again, stars is an object type that is used for raster data, right? So raster data stars, vector data SF. So the first thing we say is just data equals grid underscore R, again, grid raster that we just created above. And I just want to add a comma and say decrease the transparency to alpha equals 0.7. So if you print this, this is what we see. And it's kind of funny looking actually, because what's doing is, so each cell has its own ID, probably starting, let's see, 1 is probably at the bottom and 6,000 is probably at the top. And it is already by default coloring the grid cells by ID. And because ID is numerical, is giving a continuous scale, which again is not very useful. It doesn't really make sense to visualize it this way. But I guess the point I wanted to make here is that now we have a raster grid within the field, but outside of the field. So the raster is still there, right? But the difference now is that outside of the field, the raster cell values are NA. Remember, this was one of the things that we talked when we were talking about comparing vector and raster. So vector SF, you can have empty spaces in a vector file. That's something that happens and all the time happens. Raster is a continuous file. So even when you want to have empty space, that is coded as NA instead of just not existing altogether. So all of this area here is still a raster. There's still cells here. It's just that they're coded as NA instead of having an actual value. So remember, raster is a continuous layer, and that's why there is that difference as well.